Alright, let's begin. Alright, Madison, I can't see these numbers. I have no idea what these numbers are. You're going to have to describe them to me. So tell me about the mean of the two different data sets.
Set 1, the mean is 50, and set 2 is also.
Okay, so far there's no difference between these two numbers at all. Okay, well, help me out. How about the median? Medians might help.
The medians are also
Both 50. Okay, so the centers are exactly the same. All right, well, let's talk about spread a little bit. What'd you get for the IQR?
I got 40 and 40.
So the IQR is the same. Now remember what the IQR is. That's the middle half of our data. Okay, and they are spread out exactly the same. They're both 40. Well, maybe range will help. What do you got for range?
8.
On both? So based on center and spread, so far what we've learned in these class, these two data sets are exactly the same. Are they? Now this is the key thing. I want you to look closely into these two data sets. Are these two data sets the same? And if they're not, how are they different? Alright.
They have the same number of values.
Okay, so they both have, what, 9?
Yeah.
Okay, or 10? 9? 10. Okay, how are they different?
They, the values themselves are different.
No, how?
Like,
I'm looking more specifically. What can you tell me about how they're different, Zane?
Okay, so they all add up to the same because basically
Right.
the numbers in between, like the minimum in the first quartile and then the first quartile and the median.
The box
have
plots
same
look exactly the
ranges.
same, right? There's no difference in the box plots.
Yeah.
How are they different?
Well, they're different numbers, but they're spaced out evenly.
Ha! Okay, spaced out evenly is correct, but anybody see it? It's subtle. Yeah.
In data set 1, the numbers from 50 to 90 do they go from 50 to 90 faster? Or
Okay.
they jump larger as opposed to data set 2, they go from 10 to 50 in a bigger jump?
Okay. Dancing, you're dancing. Dance around. Yeah, what do you got?
Well, in data set 2, it jumps right at the beginning. In data set 1, it waits till about the middle.
Okay.
Median.
So you're all saying the right stuff, but in general, how could you describe these two? And I'm focused on spread here, variability.
Okay, so in dataset 2, numbers are much closer to the middle. than
Yes!
closer to the mean.
Does everybody see what he just said? Look, all the spreads are the same. The range is the same, the IQR is the same, but he just said, no, in data set 2, the scores are more bunched towards the middle. Does everybody see that now? There's only a couple of scores which do that, but the scores are, in general, closer to that 50 number than the other one. Using the words that we described, that I gave you last time we were together, variability, can we say then that this data set is more variable, more spread out, and this data set is less variable? The scores are a little tighter together. Does everybody see that now? Okay, another name for you. We'd say the ones that are closer together are more homogeneous. The ones that are farther apart, heterogeneous. They're further. There's more of a spread to them. Okay, it would be nice if we had a measurement that could snip that out, because obviously IQR and range did not do that. That's what standard deviation is. And like I told you before, it's the cornerstone of statistics. It's the most important formula that we're going to learn, measurement that we're going to learn. Let me give you an idea. Go to your formula sheets, page 3. You look at the second to the last one, you see those S's? That's standard deviation. If you go to formula sheet page 5, and you see all these crazy looking symbols here, this sigma, every one of those, that's standard deviation. You could not determine who's going to win the next election, predict the future, without standard deviation. It is the most important measurement that we do here in statistics. I'll be honest with you, when you come back in 5 years, When you come back in 5 years, I'll ask you, hey, what's standard deviation? I'd be thrilled if you can give me the answer. If that's the only thing you get out of this class 5 years later, I'd be thrilled. Now, you're going to walk out of here today, and you're going to say, what am I talking about? Standard deviation is easy to figure out. Trust me. 1 week from now, I'm going to ask you what standard deviation is, and you're going to screw it up. Okay, so focus on it, learn it, okay, and then be able to remember it later on down the line. And this is how I remember it, okay? The word standard deviation, okay, change them to words we can understand. Standard, typical. Average, but not really average, you'll see why in a second. But they're talking about the standard one, the average one. And this is the big one, deviation. Difference from the mean. We want to see how these numbers differ from the mean. Are they far away from the mean on average, or are they closer to the mean on average? That's what standard deviation is going to give us. It's going to give us a measurement to see how far these numbers are away from the mean. Okay, so from now on, when you hear standard deviation, I'd love you to just say, oh, that's just the typical difference from the mean. Okay. Got a couple of crazy looking formulas for you. I've never given this one at this time, so just forget about it, don't worry about it. But there are kind of two different formulas for standard deviation, and we'll explain to you the subtle differences of each of them. But tonight on one of your homework problems, it asks you to calculate the standard deviation by the formula. So what I'm going to show you right now is what I want to see on your paper tomorrow. So the first thing that we need to do, okay, so this is by the formula. Is write down the original data set. So let's go ahead and do data set 1. So we've got 10, 11, 30, 31, a couple of 50s, 69, that's 70, 89, and 90. By the way, this formula that I've got right here, this is the second formula on your formula sheet. It's written just a slightly different way, but the second formula, that's the standard deviation of the data set. You can't yawn in here, and you're going to yawn on standard deviation day? Seriously? All right, first thing that we're going to calculate are the deviations. The differences, all of the actual numbers are from the mean. Okay? So we'll write that this is actually the deviation. And it's the actual value, that's this guy, minus the mean. How far away are all these numbers from the middle, the mean? What'd you guys say the mean was?
50.
Madison? 50. Okay. So what is 10 minus 50?
Negative.
Careful! What is it?
Negative 40.
Negative 40. Very good. Okay, it's negative 40, right? 10 minus 50. What do we got here? Minus 39? Minus 20? Minus 19? No difference at all there, right? Those are the mean. 19, 20, 39, and 40. This data is actually perfectly symmetrical. Now, what standard deviation is on average, what is this? What would be your typical number? Looking at all these numbers, on average, how far away is the data from the mean? So what should we just do with these values? Add them up and divide by how many you've got. Don't you have the average? Do it. Uh-oh. What's the matter with you? What happens when you add up all the deviations?
0.
And they always are. I don't care what your data set is. When you go find all the deviations, they always add up to 0. So we can't just find the average deviation. Okay? Because they always add up to 0. They always will. Alright, let's think about this now. Has there ever been something you've learned in math that will just make everything positive? Absolute value. That's great. Remember the absolute value, right? You take the absolute value, it becomes positive. Well, they tried that, and they went and calculated standard deviations, but all those formulas we use it in later don't work. Absolute value is a weird mathematical property, right? Just make everything positive. Okay, so that didn't work. So is there something else mathematically that you've done in your past that will suddenly make numbers positive?
Imaginary numbers?
These aren't imaginary, right? These are all real numbers, so we don't have to worry about magic. You almost said it, though. Yeah? Square. Square?
Squares.
Square. If you square a number, does it become positive? So that's what they did. Okay? So what we're going to do next, and you see it in the formula here, first these are the deviations, and now we're going to square them all. Why? Because when I add them up, they make 0. So let's go ahead and make a column for this. Like I said, this is what's going to be on your paper tomorrow. And let's find all of the deviations squared. I can do the first one. You got the second one for me?
And the last one for you.
I do too. 15, 21? 15?
21.
I got this one. All right, 19 squared, I need that one.
360.
361, thank you. 0 squared, that's just 0, 0. 361, 400, 15 to 21, and 16. Now, somewhere down the line, we're going to have to take the square root to get these things back in reality, right? But at least we've gotten rid of all the negatives. All right, so what's this formula want us to do next? Well, let's add them up. Okay, so somebody add these things up for me. Seven, 64. All right, this number means nothing to us. Nothing to worry about. Well, what are we going to do next now? Remember, we're trying ultimately to find the typical difference from the mean. So what do you want to do next?
Divide it.
Yeah, now here's where things get really weird on you, okay? What would you think of dividing it by? What would you want to divide that by? Divide it by?
What do you want to divide by then?
How many we've got? How many we got?
10.
Okay, we don't divide by 10. We don't do what we're supposed to do. We're actually going to divide by 9. All right, I'm going to just kind of explain this a little bit to you. It's not going to make any sense. We're going to make more sense of it later. But it's called this weird degrees of freedom thing. Degrees of freedom is always how many you've got minus 1. So in this case, we had 10 minus 1 or 9. Now here's what degrees of freedom means. Don't wig out. This is not on your next test. Just kind of soak it in and see if it makes any sense. If I know the total of these numbers, and I know 9 of them, could you figure out what the other one would have to be? Yeah. So we say 9 of these numbers are free to be whatever they want to be. The last one is already determined. Okay, so that's what degrees of freedom means. Okay? So when we're doing this formula, we're going to divide by 9. Now this other formula you would actually divide by 10. This is a formula I'll explain to you later. Okay, so there is a formula that divides by 10, but it's for a different data set. So for our purposes right now, just stay with me, okay? Just divide by 1 less than how many you've got. So in this particular problem, 10 minus 1 or 9. Somebody give me a number here.
62.6.
What is that?
And 2/3.
862.667.
All right, let's just 67.
Like 2/3.
We'll just go to 1 decimal place. All right, I'm hoping third and fourth period just made me sad today. This number right here, 862.7, is something, a number, has a very important name to it. Some of you have heard this before. I haven't had one student. Every year I've got 2 or 3 students that can tell me what that number is. Third and fourth period, I got a big goose egg on both of them. Does anyone in here know what we call 862.7? Yes?
Is that the variance?
Yes! Finally! Has everybody heard of variance before? Some of you probably haven't heard of it, but the variance, okay? This is the formula for the variance. So 862.7 is the variance. It's not something we're going to use right now, but it is in our formulas later. We use the variance later. Right now, it's just the typical difference from the mean squared. Okay. What's our last step now going to be to finally get the standard deviation?
Square
Yeah, we need to square root it. Okay, so we've got this formula. We square root it. There's your formula for standard deviation. So in this problem, we have 862.7 square root. And what do we get?
29.37.
29.37. Now you're AP Stats students now, okay? It's not about can you use that formula, it's do you understand what that number means? It means that this data typically is off. I look at all those numbers and I try to find a number that describes those best. It's 29.4. Typically all of the scores are about, on average, 29.4 away from 50. Now I have a question for you. The standard deviation for this data is 29.4. Just answer in your head, I don't want it out loud. Will the standard deviation for this data be higher or lower than 29.4? Make your prediction in your head. Find out in a second. Okay, everybody got your prediction? Higher or lower than 29.4? All right, let me show you some calculator exercises. Actually, you can do this on your calculator tonight. So on the problem, you can do this math on your calculator, then write from your calculator to your paper. So I see it on your paper tomorrow. But I can show you some shortcuts on how to do this on your calculator. So go ahead. We have data set 1 someplace. Somebody got variance. I'm pretty fired up. That's good. Good! Alright, so I've got the original data. What I want to do in L2 is I want to put the deviations. The difference, all of them are from the mean. So knowing the formula for deviation, it's the actual value minus the mean of all those scores. So this is the first step, which is critical. If I want to do all these at one time, you need to highlight the top here. So whatever mathematical thing I do, it'll do it for all the numbers. So where are the original scores? This is the formula I'm using. So where are those original scores at right now? They're in L1. So just do L1. Oops. L1 minus. Now, on the very first day where we broke open the calculator, some of you found a cool place to find mean, and I showed you a cooler place to find mean, which is 1 bar stat. But right here, we can go back to that other mean calculation, and it'll calculate the mean for these, because sometimes it's a decimal, it's not as easy as writing 50 here. So to do that, if you remember, that other mean was in list. So right now, if you go second stat, then over to math, down to mean, and hit mean, it pastes that mean formula right there. I want the mean of what? I want the mean of the L1s, and close off your parenthesis. Okay, you have to have the top highlighted, and I've just done, that's the deviation formula. Hit enter, blammo, there are all your numbers that you want. Okay, so like I said, you can do that on your calculator tonight, then you can just write it on your paper. Alright, I want to do the squares, go over to the next one, highlight the top, and I want to do the squares of all the deviations. Got it? Got them all squared. I went to the top, did X squared. Got them. Okay, now you do a 1 bar stat on L3. Stat, calculate, 1 bar stat on L3. And there's our 776.4. Okay, so if you want to let your calculator get you to that number, make sure you rewrite that on your homework, though. Now you take that, divide it by 9. Alright. For the first couple of times you do standard deviation, you're going to have to show me how to do it by the formula. But then after that, you're just going to be able to go find standard deviation just by going back to 1 bar stat. My original numbers are in L1, so hit enter. There it is. Just do 1 bar stat on your original numbers. Where are your original numbers at? Just going to calculate 1 bar stat on your original numbers. And that's how you'll be able to find standard deviation. All right. Go prove your case. You guys had a prediction for your second data set. Go just use your 1var stat, do it on that data set, and see if your prediction was correct. Does the standard deviation go up for that from 29, or does it come down like you predicted? So just do a 1var stat on that data set. Mine are in L6. So I go stat, calculate on L6. 23.3. Was your prediction correct? You predicted the other way? All right, let's take a look at this now. Didn't we say that this data was more spread out? See how the 11's further, the 11 and 89, those, depending on those are test scores, aren't they further away? Okay, this gave us the 29. Now look at these scores. See how they're more bunched up? The 29 and 71, those people were much closer to the 50. So therefore the standard deviation, the typical difference, all of these numbers are from 50, is going to go down. Okay? All right, more important than just being able to calculate standard deviation, do you know some things about it? So let's talk about some properties of standard deviation. Number one, don't forget, it's the typical difference from the mean. Not the median, not other things. To find standard deviation, we go from the mean. Can standard deviation ever be zero? Don't blurt it out. Can standard deviation ever be zero? Can standard deviation ever be zero? Karen, what do you think? Never can be zero? Can standard deviation ever be zero? Jenna?
No?
Don't think so? Can the typical difference from the mean ever be nothing? What would, go back to the definition, what would make all the deviations be nothing? Casey?
All the scores were the same.
Yes, and you did good. You didn't say they were all zero. If all of the scores were exactly the same, let's say these were all 40, what would the mean of them be then?
40.
So what would the difference from all these values be from 40?
Zero.
These would all be zero, you're squaring zero, you're going to end up with zero. So yes, standard deviation can be zero. Can it ever be negative? Can we get a standard deviation that's negative? Marika? Why not? You're right. Why not? Why can standard deviation never be negative?
Because you're looking for the distance away from the...
That's one way of looking at it. How about with the formulas? Why could you never get a negative value out of this thing and how we calculate a standard deviation?
the square root.
Yeah, eventually, but then we square everything and then take the square root. So you're right. You can never take the square root of a negative, right? You knew it from there. But also we squared everything, so everything became positive. No, you can never. And you said it right. We're trying to figure out the typical distance, if you will, from the mean. Distance is always going to be positive. All right, this is a biggie, and this, you guys are still getting confused on this word resistant. Standard deviation, we say, is not resistant. What does that mean? If this number up here, instead of 90, was 90 million, standard deviation would go crazy. It would go crazy. I mean, let's think about this. Now this number is 90 million. And now we have to find the difference of 90 million from the mean, and then square it and all that, right? So standard deviation is not resistant. We found out in our homework last night that the IQR was resistant. Remember, IQR is another measure of spread, like standard deviation. If this was 90 million, IQR is still going to be 40. But if this is 90 million, standard deviation is going to go crazy. So it brings us to our next point. Okay, so your job is to describe the data to some people. Okay, well, what do you use? I mean, let's say you're just really trying to use the best statistics you can to describe the data. When would you use the mean and standard deviation? Or when would you use the median and the IQR? Here's kind of the general rule for you. If your data is somewhat symmetrical, in other words, no real necessarily extreme values in one side or the other, use the mean to talk about center and use the standard deviation to talk about spread. Mean, people understand average. You tell somebody the average of a bunch of numbers, that's more understandable to them. Use that. The standard deviation they're probably not going to know, but hopefully you can describe it to them, give them a general idea of what it means. However, if the data has got a crazy skew to it, like home prices, we already talked about how we use the median for home prices, right? The mean's going to go crazy on those billion-dollar homes. Well, we want to use the IQR for spread because it's not going to react to those either. Both of these guys go nuts. Both of these guys aren't resistant to those big values, whereas these guys are. So use the median and the IQR. Now, in your write-ups for now, you give me everything. Okay, but if you're ever asked a question, which you will be tonight, which one's better? Okay, that's your rule. All right, last thing I want to talk about is this thing called mini-tab output. Go to the bottom of page 48, please. Bottom of page 48. See the word mini-tab. Here's what they're going to do May 15th. They only got 3 hours to give you this test. So on some of the problems, instead of give you 500 numbers and expect you to put them all in L1, that's all the time that they've got to give you the test, they're going to give you like the 1-bar stats for it. And then you've got to start making decisions on what you want to talk about. So the 1-bar stats kind of stuff you get is in this thing called a mini-tab output. So let's take a look at it. You should be able to recognize some of the things in here already. That bottom box on page 48. First thing is N. That's how many numbers there were. The mean, good. The median. Trim mean, don't worry about that. We don't use that in this class. Standard deviation, that's huge. We got that. Standard error of the mean, don't worry about that yet. You'll learn about that later. And down below you've got your parts of your 5-number summary. The minimum, the maximum, and the different quartiles. Okay? So often you'll get a mini-tab output and then answer a bunch of questions. You know, what do I use, the mean or the median, to describe the data and all that stuff. Okay, you have a problem like that. Questions on standard deviation. The typical difference all of the numbers are from the mean. Anybody? Yeah?
Well, how do they? You said they use this for elections. Like, how do they?
Yeah, what I'm saying is on page 5, you see all those crazy formulas on page 5, and you see a whole bunch of this symbol. Okay? These are the crazy formulas that we're going to use to try to predict the future and stuff, which we're going to learn about in the second semester. So without this measurement, all the stuff we're going to do later doesn't work.